Welcome to another week at CosmoQuest, where all the rocket launches happen on the weekends.
We also have results from a community science project, and I have a glitching camera that makes me look like Max Headroom, so that's exciting.
But I have good news about Ingenuity that we didn't know we needed, and my camera is not glitching.
True. And then there's this wild black hole that suddenly brightened and may change how we think about black holes in general. All that and more right here on The Daily Space. I am your host, Dr. Pamela Gay.
And I'm your host, Eric Mattis.
And we're here to put science in your brain. One of the core pillars of CosmoQuest is community, and within that pillar, we try to bring together community members and science projects. That's a big reason why we're going to, spoiler alert, take off a chunk of this summer. We want to bring community science back to CosmoQuest. In the meantime, we can share results from others working with their communities to do amazing science, such as this first story that looks at results from the Hubble Asteroid Hunter Project. Those results were published in the Astronomy and Astrophysical Journal, and they detailed the finding of asteroid trails and images taken by the Hubble Space Telescope. Now, some of you are wondering how they used the Hubble, that glorious workhorse telescope that brought us several deep field looks at our universe, to find asteroids close to home. Here's a quick summary. The project involved over 11,400 community astronomers looking at more than 37,000 composite images taken by Hubble from April 2002 to March 2021. The astronomers set out to identify asteroids based on their light trails, which appeared as streaks or curved lines in the images. From that run of images, the community identified more than 1,000 possible trails of asteroids, and those detections were used to train a machine learning algorithm. Overall, 1,701 light trails were discovered in the 1,316 Hubble images. Of those roughly 1,700 potential objects, a third were attributed by the Minor Planet Center to known asteroids, leaving over 1,000 small, faint potential asteroids. Most are allocated in the main asteroid belt between Mars and Jupiter. These trails can now be used to calculate orbits, size, and even rotation periods, despite the fact that many can no longer be found with Hubble as too much time has passed between image collection and identification. With a little maths, however, even that is a problem that can be solved. It really is fantastic what community scientists can do. And now for some rockets. Eric?
There were 3 launches over the weekend. First up, a Long March 2D took off on May 5th, carrying the Julian 1 Confu 1C imaging satellite and 7 other smaller satellites from Haiyuan at 0238 UTC. This launch debuted a new style of payload attach mechanism to fit the 7 small sats below the larger main satellite in the rocket's fairing. The purpose of this is to completely use the rocket's mass capability to orbit. Second, SpaceX launched 53 more Starlink satellites on May 6th at 2142 UTC, which was another 12th flight of a booster, 1058 in this case. It has launched 7 Starlink missions, among others. This launch also marked the 117th first stage landing, this time on the A Shortfall of Gravitas drone ship. This last launch over the weekend was another Chinese launch, the 4th Tianzhou resupply craft for the China space station, and we have video for this one. Let's watch the launch.
点火！ 助推器关机，助推器分离。一级关机，一级分离。
Tianzhou 4 launched on May 9th at 1756 UTC on a Long March 7 from the Wenchang Satellite Launch Center in Hainan Island. 6.5 hours later, Tianzhou 4 docked to the Tianhe module, which is currently uncrewed. It joins Tianzhou 3, which is docked to the other end of the core module. Tianzhou 4 carried about 6 metric tons of supplies to the station, which will be used by the Shenzhou 14 crew as they prepare for the, quote, construction phase of the station, where 2 more modules will be launched and docked to the station. China expects 5 more launches in support of its space station program this year, 2 crewed spacecraft, the 2 modules, and 1 more uncrewed resupply spacecraft. Similar to Progress and Cygnus, Tianzhou will be filled with trash and deorbited into an empty part of the ocean at the end of its mission. This Long March 7 launch campaign was quicker than the last, taking only 27 days. According to Chinese sources, the rocket has 17 improvements, and the countdown was also quicker because both propellants were loaded into the vehicle simultaneously. This too launches the past few days for the 419th and 420th Long March family launches. Those are all the launches from the weekend. Now for one more piece of spacecraft news.
With all the issues various spacecraft have had in the past couple of years, it's nice to report on when something gets fixed. Of course, it helps that most of us didn't know it was broken to begin with, so yay for good news we didn't know we needed. Last week, our favorite little Mars helicopter, Ingenuity, missed a planned communication session with the Perseverance rover. It was the first time an issue of this nature had occurred between the Mars exploring pair, and as Percy is Ingenuity's link to Earth, fairly troubling for the operations team. But as we said at the top of this story, the news is good. Ingenuity is talking to Percy again, and the ops team believes they have determined the cause of the anomaly. To very few people's surprise, I'm sure, the answer was, as always, dust. The helicopter's battery went into low power state because of diminished sunlight hitting the solar array. That triggered another array, which handles Ingenuity's operational state, to power down. And that reset the internal clock and powered down the heaters. Whew. Then the sun came up, the solar array charged the batteries, everything turned back on, and that pesky clock was no longer synced with the one on board Perseverance. The ops team set Percy to just listen for Ingenuity on May 5th, caught the signal, and rejoiced that everything was back to nominal, for the moment at least. There are growing concerns about how Ingenuity will manage during the oncoming Martian winter as the dust storm season approaches. The operations team is working on a plan that they hope will keep Ingenuity up and running. And team lead Teddy Tizantis is optimistic, saying, quote, "Our top priority is to maintain communications with Ingenuity in the next few sols, but even then, we know that there will be significant challenges ahead. I could not be prouder of our team's performance over the last year, let alone our aircraft's incredible achievements on Mars. We are hopeful that we can accumulate battery charge in order to return to nominal operations and continue our mission into the weeks ahead." End quote. Good luck, Ingenuity. Stay warm. Coming up next, a galaxy whose black hole had a surge in brightness may shift how we understand black holes in general. Stay tuned. There's a running joke in astronomy that pretty much any talk can be thwarted by the simple question, what are the effects of a magnetic field? I've known that joke my entire career, but I thought I had a good enough understanding to get the feel for things, magnetic fieldy things, until today. My mental line drawings didn't leave room for the concept of black holes somehow reversing their magnetic fields, and now, somehow, a team led by Subhashi Laha of NASA is suggesting this is exactly what some supermassive black holes in active galaxies are doing. Let's back up. Here on Earth, we know from geological records that our magnetic poles generally wander about a bit, and every 200,000 years or so they flip. Our magnetic field is driven, in the most simplified terms, by convecting hot metals setting up loop after loop after loop of essentially electromagnetic fields and together aligning to create a single averaged out planetary magnetic field. It is possible for those loops to get out of alignment and, in the ensuing chaos, for their orientations to rearrange so that the magnetic field overall stays aligned, sort of, with the Earth's rotation, but the specific north versus south magnetic field flips. In my personal mental model, I always imagine one of those wild Ferris wheels where each car is free to rotate and the entire wheel is also rotating. Small factors can add up to influence the cars to mostly go round and round and round one way or the other. But both rotations are possible within the mechanics of the overall rotation. I also just like to think about riding roller coasters. Anyway, that's my mental model, and it stands up for thinking about the Earth and the Sun. But as we get out toward the kinds of magnetic fields that are associated with disks of material orbiting compact objects like neutron stars and black holes, my gut instinct, which is a lying liar at times, said we should have one orientation and it should stay put. And from looking at the literature, there isn't exactly a thriving community of folks modeling what would happen if a black hole's magnetic field flipped like the sun's magnetic field. But there are papers asking, what if? Not many, but some. And there's also a weird thing sometimes observed in active galaxies with feeding black holes. Occasionally, these systems will brighten by nearly a factor of 100 and then fade back to normal over just a few months. Called changing look active galactic nuclei because they change how they look, and astronomers are terrible at naming things. A new paper led by Subhashi Laha describes the brightening as a symptom of the magnetic field reversal at the central supermassive black hole. This work is accepted to appear in the Astrophysical Journal. Using computer models and observations spanning from long radio wavelengths of light through to the super short X-ray colors, this team could test different theories against the data. They ruled out the idea, which I liked, of black holes eating stars. The light profiles and timing just didn't match. Instead, what they say, according to Jason Dexter, was, quote, the field initially weakens at the outskirts of the accretion disk, leading to greater heating and brightening in visible and UV light, end quote. They also saw the X-ray light turn off and then turn back on. This detail matches the specifics of a magnetic field reversal, where, to quote the NASA press release on this work, quote, as the flip progresses, the field becomes so weak that it can no longer support the corona. The X-ray emission vanishes. The magnetic field then gradually strengthens in its new orientation, end quote. Why do some black holes flip their magnetic field? No idea. What causes this behavior? Still no idea. Do we need to worry about our supermassive black hole in our galaxy reversing its magnetic field? Probably not, but that is a gut feeling. And again, my gut is a lying liar. In every astronomer's life, there comes a day when the full weight of how little we know about magnetic fields suddenly weighs heavy. For me, today was that day. The universe is weird. I love to watch it. And I am grateful there are people working to get at the maths behind all the wonder we see. People who are not me. Okay, before we chat about Mars, I think we need a pretty picture of that wondrous universe. If you have a small telescope, you may have enjoyed looking at the fuzzy blob M99. This not too distant galaxy is highlighted in a NASA image released this week. Combining data from multiple studies of this galaxy, this image allows us to take in the range of star formation, dust clouds, and brilliant stars that make up this system. There's no new science here, just the galaxy with all the prettiest stars. From Galactic Horizons, let's come back to our solar system and an interview with Cathy Weitz about the horizons of Mars. Stay tuned.
Last week, a press release was issued from the Planetary Science Institute about an intriguing darker layer of rocks on Mars at Mount Sharp, near where Curiosity is roving. This layer is darker, stronger, flatter than the surrounding sulfate-bearing rocks and has been observed using orbital data from the HiRISE camera on board the Mars Reconnaissance Orbiter. The layer is also weathering differently than the layers above and below, suggesting it is made of a more erosion-resistant rock. This discovery, of course, leads to the obvious questions about why and how that layer is different. Joining me now to talk about possible answers to those questions is senior scientist Dr. Cathy Weitz, lead author of the paper published in the Journal of Geophysical Research Planets. Thank you for being here today, Dr. Weitz, and welcome. So, tell me about this marker layer. Can you just sort of give our audience a brief overview of what it is specifically that you've discovered?
Yeah, sure. So everybody is aware that in 2012, the Curiosity rover landed in this 155 kilometer diameter crater called Gale. And so the rover has been sort of making its way up this big mound in the center of Gale called Mount Sharp. So what we've been doing is trying to, we've looked at all these orbiter images of Gale, and, we see these different interesting features, and then we try and, as the rover drives across them, try and figure out, what did we see from orbit? What did we predict we would see? And is that what the rover is finding as well? So we've done pretty well. We sort of predicted that there were these fluvial sediments that formed in a lake within Gale. And, we found those kind of laminated mudstones and sandstones already. And now we've been driving up into these clay-bearing sediments. So we saw these clays from orbits, and now we see them from the rover. And we're starting to make our way into what we saw are these sulfates. So we see them in orbit, these sulfate-bearing strata, and now we're waiting for Curiosity to finally say, yes, I've seen these sulfates now from the ground. So that's what's been happening with the rover. And then as the rover keeps driving up Mount Sharp, it's going to eventually cross paths with this kind of dark tone, and as you said, this sort of hardened layer that we can see it from orbit. And so we tried to, look at data from orbit to figure out what it could be, because it definitely stands out. It's easy to trace along, 80 kilometers of distance through Mount Sharp. And so we put together a couple hypotheses of what we think it is, but I think it's really, we're going to have to wait until the Curiosity rover gets there, because it's got some instruments where it can look really up close, like a field geologist on Earth, where you break out your rock hammer and start pounding away and try and look with your little microscope up close at the rocks and try and measure what minerals are in it. And then once we do that, I think we'll have a much better sense of why this kind of rock stands out compared to all the rocks around it, what made it so different.
So why are we calling this a marker horizon? What does that term imply?
So on Earth, this is a term that we use on Earth called a marker horizon or a marker bed. And it means this is like something that stands out compared to all the rocks around it. And you can trace it for, long distances, tens, hundreds of kilometers. So like on Earth, when there's a big volcanic eruption, it produces ash, like a couple centimeter thick ash bed. And so you can walk all across, a long distance and find that ash bed. And so, wherever you see that ash bed, you can figure out what rocks formed before it, what rocks formed after it. So like for people out in the Northwest, Mount St. Helens produced this marker bed of ash. And so you can find the ash from the Mount St. Helens eruptions. And that's something that, would stand out compared to the other rocks around it. So it's considered a marker horizon.
Right. I remember from my own field work in undergrad that, we explored the Bishop Tuff, which, you could walk through just about everywhere in the Mojave and find. And so it was great for sort of understanding where you were in the stratigraphy. Okay, these rocks came after, these rocks came before. We kind of know where in time we are. So what we're looking at is a potential marker bed on Mars that can tell us sort of the same thing. Something happened at a uniform time, and now we can sort of say the rocks below came before, the rocks above came after, and it splits something for us. What are some of the hypotheses on this marker bed for why it is eroding differently?
So it clearly it must be harder because it stands out like as this nice flat ledge. So you're going down slope, and then you get this flat ledge, which is the marker horizon, and then it goes down slope again. So in order to get that kind of nice flat ledge, it must be more resistant to erosion. And so, there's a couple ways you can, get something more resistant. It could have like more cements in it, like salt. If it's got a lot more salt and the water that brought it through caused all the cementation with those salts, then that could make it harder than the rocks above and below it. It could have just have larger particles in it. So the bigger rocks inside of it, like, centimeter boulders or size, that kind of like that, compared to more smaller grains that are above and below it in those rocks, that could make it more resistant to erosion. But in any case, it's definitely, we know that it's hardened from some kind of either when it formed or after something happened to it after it had formed that made it harder relative to the rocks above and below it.
So is it possible, and this is kind of me just sort of speaking here, is it possible that this could be some sort of volcanic layer?
Yes, so there are four possible reasons why we think it could have formed, at least based upon the orbital data. Keep in mind that once we get there with the rover, it might be something completely different that we never even thought of.
Right.
But for now, yeah, ash certainly. We know, Mars is a very volcanically active planet. There are a bunch of bigger volcanoes in that region. And we know on Mars that because it's thinner atmosphere, when you have a big explosive eruption, the ash will travel much further than it would on Earth. So you could, deposit ash, and it could have gotten laid down in gale while we were forming these sulfates. And so that's why you have it there. So it could be an ash layer. Another thing is that it could be a sandstone. So like if gale it got drier, you could form, you'd have sand grains forming dunes and whatnot. And so that could have then formed a more resistant unit, because we have seen other sandstones in gale, and they do stand out as being more resistant than the other sediments around it. So it could be sandstone. Another possibility is that it is the same sulfate like that above and below it, but somehow there was more water that that brought in more of these cementing agents like salts. So for some reason, this layer in particular got more salts, and so it became hardened relative to those above and below it. So there's definitely a couple ways we think it could have formed, but again, with the orbital data, we have a lot of limitations on what we can really see and tell.
Right.
So that's why we're really looking forward to Curiosity getting there.
Do we have any idea on the possible age of this layer, or right now are we still just in sort of comparison to the other layers mode?
Yeah, so we're definitely trying to compare it to those above and below it. I mean, we know that most of these sediments in it is probably formed, well, Gale Crater formed probably around 3.6 to 3.8 billion years ago. And so we know that the sediments that formed in it must be that age or younger. And so, as you work your way up, you're getting to younger sediments. So, we're probably dealing with more early Hesperian, so that's, younger than 3.6 billion years.
And you mentioned water could be involved in this, so this was a region that had water on it too?
Yeah, so we know that, these finely laminated mudstones and sandstones that we've already seen with Curiosity, that those definitely formed in kind of this what's called an alluvial fluvial deltaic lacustrine. So there's just a lot of different processes operating, but they all required that there be water. And so the sulfates also, those require water to form. So we know that there was water around at this time when the marker bed formed.
If you were to pick an Earth analog to compare to Gale Crater or even this marker bed, what would you use?
So I would definitely use these volcanic ashes, as an example of how it formed. As I said, we definitely on Earth, when we have these big eruptions on Earth that deposited ash over a wide area, it forms this really nice marker bed. So, I do think that that's a great example, but we have seen on Mars that drier conditions like sandstones, when they form with less water, that they also can produce, a marker horizon like this. And so on Earth, we've definitely seen, when you look in the rock record, you can see a lot of sandstones that also stand out, but they tend to be they don't tend to cover as large an area, and they tend to be more kind of undulating in their surface. They vary in their thickness, whereas the marker horizon that we have measured from orbit, it seems to be constant in its thickness. So that's the reason why we're not really favoring the sandstone origin right now.
Do you have any idea of how long it's going to take Curiosity to get to sample your marker bed?
Not at this time. The rover was supposed to be driving across this, what's called green hue pediment. But I don't know if you've seen the news lately. We found these really difficult rocks to drive over. They call them, like gatorback, because they're just very rough, rugged rocks, and Curiosity has the damage to its wheels, and so we want to avoid, driving the rover over these really rugged rocks that could, bust up the wheels anymore. So the rover recently had to turn back and drive off this pediment surface, and now we're in this clay sulfate transition region, and I think a lot of people still hope we can make our way to the pediment, just to the edge of it, though, as we go upward. So it sort of depends upon how much kind of time and effort we want to make towards getting back on that pediment at a different location versus going uphill. We're only about, we're less than a kilometer away in distance from the marker horizon, but depending upon how much time the team wants to spend, and as we drive up to it, that could determine just how long it takes. But I'm hoping it'll be, in the next, 6-8 months or so.
Fantastic. Well, once again, thank you, Dr. Weitz, for taking the time to speak with me today. I'm really interested in learning more about this marker horizon and the implication for Mars's geologic history. So thank you again.
Oh, thank you so much. I'm glad to have been here, and thank you for your interest in the paper I had.
This has been The Daily Space. To all of you watching, our conversation ran longer than we can air here on Now Media, but you can catch the interview in its entirety on our website, dailyspace.org.
While you're there, check out our show notes to find more information on all our stories, including images. As always, we're here thanks to the donations of people like you. If you like our content, please consider joining our Patreon at patreon.com/CosmoQuestX.